plenty of quantum operators which map one qubit to one qubit, and there is actually an infinity of such operators. But there are only 4 functions which map one bit to one bit, and we are going to implement the quantum operators for each of these functions. And we start with the constant f of x equals to 0. Now the operator for this function acts like this, and this f of x equals to 0, so it's just x, y for any vector, so UF in this case is just an identity matrix, 4 by 4, of course, because we have 2 qubits here. And the implementation of such matrix on a circuit is quite simple. It's just nothing. Okay, we'll continue with constants. Let f of x be 1. UF acts like this in this case. So it always flips this lower qubit, and the scheme is going to be this for this operator, and the matrix is this, which is y times the product x. Well, let's continue with the balanced functions. F of x equals x. Now we are going to consider different vectors. Now 0, 0 maps to 0, 0. 0, 1 maps to, again, 0, 1. 1, 0. Now we have x equal to 1. And we add this one here, and we have 1, 1. And of course, 1, 1 maps to 1, 0. And you perfectly know this operator. It is just C naught. And even more fun with f of x equals to not x. Let's see. 0, 0, now not x is 1. It maps to 0, 1. And 0, 1 maps to 0, 0. Now 1, 0 is untouched. The same as 1, 1. And those of you who did the exercises for last week perfectly know this operator. It is this contra C naught, which is like the operator with this matrix, and the scheme of this operator is this. The circuit of this operator is this. Now let's proceed to the algorithm. So here is the circuit scheme of the Deutsch algorithm. As you can see, we pass 0 to the most significant qubit, to the argument qubit, and to the value qubit we pass 1. Then we apply Adamar, and only after that we apply our quantum oracle, quantum black box, in which sits one of these things here. but we don't know which one. So in quantum case, before we query the oracle, we make some clever preparations, and we query the oracle only once. And after that, we again apply Adamar to the input register, and then we measure the input register, not the output. Looks a bit intricate, so let's see how it works. So here is the scheme. Let's apply it. Now we have this 0, 1. After Adamar, it would be 0 plus 1 with this vector plus and vector minus. We can write it like this. So we are here now, and it is time to apply the oracle. And you remember that for this state, the oracle works like this. So it's 1/2 minus 1 in power f0, 0, minus plus 1/2 minus 1 f of 1, 1, and minus again. Well, now we are here. Let's combine these values in the scope. So it's again 1/2. Now it's minus 1 f0, 0, plus minus 1 f of 1, 1. And here is this vector minus, which is not anymore interesting to us. We are now interested in this first qubit because all the actions here are applied to it. Okay, imagine that f of x is a constant. Then these powers of minus 1 here are equal. F of 0 equals to f of 1. And we can put it away from this scope. And here we have just vector plus. And after we apply Adamar to it, it will be 0. And if f of 0 does not equal to f of 1, which is true for any balanced function, then these powers is going to be different. And we have here vector minus. And after Adamar, it will be 1. So for a constant function, we get 0 in the input register. And for a balanced function, we get 1. So we can easily distinguish them. And we still don't know which function stays here in this quantum black box, so we don't get this extra information, and we obtain the result in 24 hours because we query this oracle only once. On this slide, you can see the implementation of Deutsch's algorithm on a quantum computer simulator developed by my student Yuri Konoplev. And you can see the UF operator here is C0, so it's identity function, f of x equals to x. And no surprise, we get 1 here. And actually, we don't need this Adamar here. Now, this quantum simulator is available on the link QC sim app spot.com, and you can find this link below the video. Now, what is the trick here? We have introduced something more complicated than a classical oracle. Classical oracle takes only 1 bit, and this thing takes 2 qubits, and we pretend to solve the problem more effectively. At this point, it may look like this, but let's go further.